So good morning again. Again, for you, mostly more or less exotic topic, because most of you are interested in ionosphere, plasmasphere stuff. Still, I'm going to try to motivate you a little bit to look into the thermosphere as well. So yesterday I gave some let's say, the global structure and global drivers. Today I will focus on one of the empirical models. That said, essentially the algorithms of the empirical models are the same. So if you compare DTM to MSIS and even JB, a little bit different, the algorithms are the same. These models, like I said yesterday, they're simple, they're fast, they're very robust, and so they're mainly developed and maintained for orbit determination and extrapolation. So in the outline, I will discuss so atmospheric drag. So how do we compute the drag? What do we need to compute drag and forecast drag? Then empirical modeling. Sorry, errors in the data and the drivers. So that is what handicaps a little bit our ability to create accurate models as well as forecast accurately thermosphere and drag into days, weeks into the future. That's in the forecasting part. I'm showing a little bit what the uncertainties are on the time scales that we have required for day-to-day business all the way to mission design, so where you need like one up to several solar cycle prediction and see the effect on your mission. And then finally a last slide on, okay, how does this, what causes all these effects on when you're trying to elaborate a model. And then I will show quickly how you can run the model on the eScience Center. So drag. I guess all of you know, of course, any object in space in low Earth orbit, let's say below 1,500 kilometers, will ultimately re-enter in the atmosphere and burn up. So when we compute these re-entry, when it's imminent re-entry within let's say within a couple of days, we extrapolate the orbit based on forecasting of drivers and with our models to the contact point, which is 80 kilometers altitude, because that's where the atmosphere becomes so thick that essentially most of your spacecraft burns up, depending on how big and how solid the spacecraft is, of course. But from that point on, you can essentially all the remaining parts from the contact point 8 more or less drop vertically to the ground. So that's why you compute to 80 kilometers. Then you know more or less if there are debris reaching the surface, it will be in a small circle around that contact point. So in this example, what you see here, this is time, years, since beginning of the mission of CHAMP in red, GRACE in blue. So you see here, GRACE had stayed very long at a relatively stable altitude. And then here for CHAMP, it re-entered in September 2010. You also notice, of course, you had these steps in the mean altitude, and these are orbit raising maneuvers. So that is typically when you are propagating your orbit into the future. You want to know how long your mission is going to stay up in space. And once in a while, based on models and forecasting, you do these raising maneuvers to maintain your orbit for the design period of the satellite. So this is the satellite drag acceleration equation, the basic one. So you have CD, which is aerodynamic coefficient, which is the coefficient that relates the particles impacting on the surface. So it's the how much energy is transferred by the atmospheric particles on the surface of the satellite. So this CD is also through a model that we obtain this value. Then we have the ram surface, so that is let's say the frontal surface if the satellite is flying in this direction, which is the case for these two. The mass of the satellite, Then we have rho, which is the thermosphere density. So that is the part that also comes from your model. So in this specific case, one of the empirical models. And then, of course, we have the speed of the satellite, which you have access to the speed through the orbit termination process that gives you precision and speed of your vehicle. And we do that always with respect to a co-rotating Earth atmosphere. So we do not take into account winds because for two reasons. One is the effect is very, very small, and secondly, the wind models are often as bad as they are good, and so most of the time we have no benefit of actually applying wind models. So this is what I showed yesterday. A thermosphere model, if you take an empirical model, at each position of the satellite, actually you're going to compute one density along the orbit. So you input a date and a position, so altitude, latitude, longitude, solar local time, and the drivers. So depending on the model, in this case DTM, we're using F10.7 radio flux and geomagnetic activity KP. MSIS is about the same. If you take JB, they have a different solar driver. They have a mixed geomagnetic drivers. Again, like I said, they're easy and fast. Disadvantage, of course, this comes at a price, this fast computation. It has low resolution. It's a climatology model. It gives you a specification of the atmosphere based on their underlying database. So it gives you the mean state of the atmosphere based on the data set that you have used to fit your model to. So if you're computing this kind of model using data from 1960 to 1980 and 2000 to 2020, you will not obtain the same model. It's actually, these are semi-empirical models in the sense that we do not just fit polynomials or whatever to the data sets that we have. We know from theory a number of variations in the atmosphere that we know should be in the data that we are ingesting. So typically periodic variations, so that's the diurnal, semi-diurnal, terdiurnal, so that's the effect of the Earth rotation with respect to the sun, so that's the local solar time effect. Then we have the seasonal variation, so annual, semi-annual, that's the effect of the orbit of the Earth around the sun, which is a little bit eccentric, and the semi-annual effect is because the Earth inclination, the pole is a little bit inclined. Then we have a certain number of non-periodic, so we have latitudinal variations, which do change with season, by the way. We have the drivers, so the energy input from the sun through either F10.7 or one of the other drivers. We use that as a direct measurement, as well as the average of the last 81 days, so 3 solar rotations. That gives us a little bit more stable regression if we use that kind of long period behavior and superpose a little bit of faster behavior. Then the geomagnetic activity. So KP, we use that most of the time delayed by 3 hours, or in case of MSIS, for example, you use several delayed values of KP going all the way back to 48 to 72 hours in the past. And you use also a kind of a mean value, so that gives you kind of a preconditioning of what happened before the storm. All these effects, the periodic effects, and you couple these with solar activity. So these amplitudes are also modulated by solar activity. So here's the algorithm. The density at altitude Z is computed by projecting the density at the base altitude of 120 kilometers. So if you look back to the equations I gave yesterday, so this is the rho zero. You give this at 120 kilometers, and then you extrapolate this upward with this function f in which there is the temperature. Fi here is the height function, so all the equations are given below. And this height function then distributes each individual species along its own individual height profile. And then finally, to take into account the variations I just showed in the previous slide, we have a spherical harmonic function, which gives you these diurnal, seasonal variations as well as the energy inputs. For those of you who don't know what spherical harmonics are, so typically this is the kind of basic variations that you can recover using spherical harmonic functions. Like I said, these models have very low spatial resolution. We actually only develop up to degree 4. So degree 4 over the sphere, you see about that, what the size of the maximum variation is that we can actually capture, that we want to reproduce. Anything smaller than that kind of variation, we just go through, average out. And so what I showed yesterday, these small wiggles, when we're looking at these variability of the order of hundreds to thousands of kilometers, it's what happens inside these cells, but which we do not measure, but we just fit through the middle. Let's put it crudely like that. Okay, so that's just, here's a part of the spherical harmonic function. So typically what you see here is how these functions are used. So you have a fixed part of the flattening of the Earth in the latitude structure. Here you have a part which is a diurnal, semi-diurnal variation. So you see here how these variations then are used with a coefficient that gives you the amplitude of this particular variation each time. So when we are fitting the model, what we do is we fit all these last, so all these coefficients A and rho at the bottom of the model, we fit these using our observations. So as observations, we have total densities, we have partial densities, so composition, and we have temperature, or in absence of temperature, you have to adopt some kind of temperature model. And so to drive the model, solar extreme ultraviolet, f10.7 is the most used. In one of the other models, I use another radio flux, 30 centimeters. I will show you a little bit later why. S10 is actually helium-2 line, so it's real EUV measurement. It just has been rescaled on f10.7 for convenience, so that everyone understands actually what this amplitude means, because if you go from this amplitude to this amplitude, it's very difficult to comprehend if this is a big variation or a small variation, so we put everything on the same scale. Geomagnetic activity, well, KP-AP is the same thing, and then DST is also used in JB, but in a hybrid way. So the data that we have available. We have, since 2000, we have a relatively large amount of high accuracy, high resolution data, thanks to these satellites, which were equipped with an accelerometer. So the accelerometer gives you densities along the orbit track with a resolution about 80 kilometers along the orbit. But it's just one orbit, remember, one orbit, one altitude. These missions also, they were all missions of opportunity. None of these are actually aeronomy or space weather missions. They're all geodetics, they're gravity missions. At higher altitude, we have some again, geodesy satellites, which we can track by laser, and we can infer total mean densities. But at the cost, again, we have one mean density per day. Then in the past, in the 70s and 80s, we had the mass spectrometers. So all our composition information today comes from data from the 70s and the 80s, which, by the way, we are now no longer able to calibrate, because at that time we didn't have the same precision in orbit, thanks to GPS, that we have today. So these values have to be calibrated through the model 20 to 30 years back. And so here in the middle, essentially we have no high resolution data at all. The only thing that connects us are, again, daily mean densities based on two-line element data, which span all the way back from 60 to almost to today. So what you see here in the middle, we have a big gap, and that gives us a big problem, because we have to fit in the model composition in that past, and in some way, without skewing the model, with the total densities. So the total density is the sum of the composition, which makes it a little bit complicated, and it has to agree on both sides as good as possible. Now, when you were looking at that plot, you may think, well, what is he complaining about? There actually, I saw a lot of satellites, I saw a lot of missions, there has to be a lot of data. Well, yes and no. It's not just the fact that we have this big hiatus in the middle, but if you look closer at each of the data sets, you see that this distribution within each data set is very unequal. So these are the old data, 70s and 80s. What you see here of the CNES satellite, the EMESA satellite, this was an eccentric orbit, so you see here the coverage of latitude over time, so you have unequal latitude coverage. This one was in a tropical orbit, so in a 20 degrees inclination orbit, so you have only information in this band. Cactus, accelerometer, similar. This is the distribution typically over 1 month with the mass spectrometers. Again, these are elliptic orbits, so this gives you latitude versus altitude. So this is the amount of space and time that is covered by such a mission. So actually you have more holes than information. So one of the other, one of the error sources is this sparsity of data. The other is when you are inferring data from even the modern data, the accelerometers, you have extremely accurate measurements from the accelerometer. But when you're trying to extract densities, you have to correct your non-gravitational force measured of all other accelerations that are not due to drag. So basically, solar radiation pressure, albedo, and thermal pressure of your satellites. And so if you express the ratio of, let's say, these thermal forces with respect to the drag force as a function of altitude, you see that when you are at very low altitude, of course, when density is very, very big and proportionally solar radiation forces and pressure force are very, very low, you see that here's GOES, which was at about 250 kilometers. You see indeed that the effect of the thermal forces, the radiation forces, was less than 1%. So even if you make 100% error in your radiation pressure modeling, you only have a very, very small error in the density that you infer. On the other hand, if you go up, so here we are at missions about 500 kilometers altitude, and what you see here is that typically during solar minimum years, the pressure forces are larger than the drag forces. So if you make even small errors in your pressure force of your satellite, it enters directly as an error into your density. That is something where there's nothing we can do about this, so we know that we have to take into account the error as a function of altitudes of solar activity. Second thing is when we're using the accelerometers, we have to calibrate the data. What I showed two slides ago, the MESA data and the Cactus data, those are also accelerometer data. These were calibrated using a model of the thermosphere itself. So it's biased towards one of the older MSIS models. Here, with CHAMP, with GRACE, with all the newer satellites, we can calibrate these very, very accurately, and it was done with GPS, of course, which was not available at the time. So now we have an instrument that is very accurately calibrated. Just to give you an idea what happens if you do not do this, so these are the biases that you have to apply. You see that it's absolutely not constant. This value here is actually 10 times bigger than the non-gravitational acceleration. So if you do not have correct biases, your error is even larger than your signal. Another error source. So what I said is this drag coefficient, CD. So when you see this was the basic drag equation. So when you're inferring drag from this drag equation, you see that CD here. And depending on the value of this CD, your density is effectively scaled. If you're using 1 or 2, your density will be twice as big or twice smaller, depending on which side your CD is going. And CD, remember, still is a model. And the problem with this model is that we do not agree within the community which is the best model to use. The other thing is, even when we are supposedly using the same model, we even do not interpret what the drivers are of this model entirely the same in all groups. So when people are inferring densities from drag, you get very, very different results. And that is shown here. Typically, the black line here at the bottom, these are CHEMP densities, which I derived 20 years ago. And then later on, these were derived again by TU Delft. Because they have a very sophisticated satellite model and CD model, you see the offset. It's essentially a scale, but there's a little bit more. But this offset is about 23%. So we have a 23% bias through your choice in CD. Same thing here. If you take the GOES densities at 250 kilometers, you take the same as computed by the US Air Force. You also have an offset about of the order of 20%. If you're going to use these data sets in your model, you have to make sure that you have data sets that are actually consistent. That means that if you're going from one altitude to the next, you propagate those up with a temperature profile, that you end up starting with this density, you end up with this density correctly and not with some other thing. So you can use, now that we know these values, you can use this value with the black value and the light blue with the red, but if you do it some other way around, you're introducing a 20% bias in your fit somewhere, which the model, through least squares, has to absorb somehow. Now we have differences in shape. You would say, well, this is a relatively easy problem to solve. Not even this is well, of course, as a sphere is exaggerated. That said, it is still being done for debris, for example. Sometimes we do not know what the exact shape is. But if this is the exact shape, well, you could do it like, typically Delft would do it this way. So a finite element model with thousands of elements. You could do it this way, which is, you could say, well, it's already pretty close, or you could this way. But each time, there will be small differences. Of course, these differences will be more of the order of a few percent, but even this, between this and this, it can also be 20%. So even the satellite shape is something that is a little bit complicated, also through the fact that this detailed drawing we do not always get from the industrial partners. If that is not agreed upon before launch, it is very difficult to get this kind of sketch. Just to show you what this CD can do. Like I said, it can give you very different results. For CHAMP, all these all these colors are just different models. And it's not the most different models in the world, so the differences can even be larger. For CHAMP, which is at 350 kilometers, if we go to lower altitudes, the models start to agree. For this instance, with these models, we only had a few percent difference in offset in the CD. But if you go a little bit higher up, for GRACE, with respect to this in the middle, his is 13% smaller, this is 17% bigger. So you can have a huge spread in density that you're going to assimilate due to the fact that you have selected a density data set that has been selected with this value or with this value. So you absolutely need to know from your data provider how it was calculated exactly. Another error is, of course, the driver. Like I said yesterday, what you're using is a proxy. So it's a measurement that mimics variations of another observable. In our case, we want something that reproduces, it is closest to the variability we see in EUV. EUV is a big term. EUV is not just one line. EUV is also part of a spectrum. So of course, in the past, F10.7 sunspot number and then F10.7 were selected to represent this variability simply because here at the surface of the Earth, we cannot measure EUV. So F10.7 was used as something measured from the ground that has high correlation with actual EUV. like I said, so here's the EUV spectrum, what I think I showed yesterday as well. So here you have some strong lines, iron 15, helium. This is the EUV part. Let's say these proxies, these work because they're actually produced more or less at the same altitude in the solar atmosphere. So they come from the chromosphere, lower photosphere. So they're all generated at more or less the same solar altitude. That's what we're looking for. And that's why these indices are quite well correlated. But, like I said, this is both EUV. So here you have iron 15, and here you have helium 2. And you already see that even the spectral lines this close together can have a behavior that is very, very different. And now you want to try to capture that transitional behavior of a whole bunch of lines in one single number, your proxy. So this proxy is sometimes right, and sometimes a little bit less, and sometimes it's wrong. That also enters into your model error. That is something, on the other hand, that we do not know. So we have done tests in the past to look for the most representative proxy as a single value for EUV. When we did this, we didn't have F30 to begin with, and we did this test on several time scales, let's say half a solar rotation, and let's say solar cycle scales. And always, like this plot is actually showing, it's a correlation which means you have to read it as the closer one of these parameters is to your looked for parameter rho, the higher the correlation is. So in all cases, actually, S, which is helium-2, gave us the best results. Still, we didn't use that because of very serious calibration issues, which I can show you a little bit later. So we looked further, and we stumbled more or less by chance on F30, which has been measured in Japan since the 1950s. They just never told anyone. So here you have the 30 centimeter radial flux, here you have 10.7, and here you have helium-2. And we found out this higher correlation with EUV through the composition, like the contributions of Bremsstrahlung, gyroresonance, and free electron combination. And so you see that typically Bremsstrahlung and gyroresonance between F30 and helium are relatively close, whereas the F10.7 contribution of these three components is indeed very, very different. So that is why we explain the fact that F30 is indeed much better correlated with EUV than F10.7. So for the geomagnetic drivers, here also, the errors are due to several reasons. First, again, of course, it is a proxy. You give one single number that is supposed to give you the information of the energy input on both poles. You give that number only every 3 hours, or DST every hour. This measurement KP is measured, as was shown yesterday as well, by a very asymmetrical network. So you have most stations in the northern hemisphere and you have only a few in the southern hemisphere. It was said yesterday about KM. KM actually not better at all. For some strange reason, and maybe because Bartels did his conversion tables from the stations to the actual perturbation much, much better than what's done for KM. I did the test, and actually correlations with KP is slightly better than with KM, surprisingly. And then you have DST. So the KP is most used, again, because it is easy to use, it is very robust, it is operationally always available because there is a large number of stations. So like I said, it's a planetary index. So each of these numbers gives you the total input over 3 hours over the planet. If you take the physical models, what I showed you yesterday, TIE-GCM, WACM, or whatever, they're using a different input. It can be AMI, which is the most sophisticated. So there's assimilative mapping of ionospheric electrodynamics. So this is actually a model that assimilates data in real time, so that should be the most accurate. You have the Weimar model, so these are the statistical patterns that are modulated also with geomagnetic activity. So these both are much more representative, more accurate than the simple KP. Still, even if you compare these two much more accurate models, these plots here showing North Pole of electric field. So here's the AMI output, and here's the Weimar output. Just show you for it's not even a big storm, it's just a minor storm. Just look at the difference of energy input and location. So even if you use Weimar or with the Weimar model with respect to KP, sometimes you do not gain that much. AMI is a different story, of course, but not many models can actually run with AMI because it's a little bit complicated interface. So here also, we've been looking for more representative, better indices for geomagnetic activity. And in a previous H2020 or FP7 project, we, GFZ developed a new index called HP. And specifically, it's called HPO. HPO means like it's open-ended. So it uses the same algorithm as KP, so the same kind of maximum, so the range index within a certain window. This time the window, on the other hand, is 60 minutes or even 30 minutes. So we have higher temporal resolution. It's still a planetary index though. But it has become open-ended. You have to know that, or you should know, KP is a capped index. When it is measured and it is larger than a certain threshold, KP is 9. If it's twice as big, it's still 9. If it's 10 times as big, it will still be 9. It was designed that way in the past. It means, on the other hand, that you have no information if there is a real superstorm. Your output will always run with KP9. HP now is like DST. It has no capped value. So when GFZ recomputed the HP values for the Halloween storm, which was a double peak at KP9, now the maximum peak is like more than 11. So here it gives you a much more realistic impression of what the real energy input was at the time. Secondly, of course, when you're switching from 3 hours to 1 hour to 30 minutes, you have a much better timing of the storm. So typically what you see here, if you have KP, you would have something like this. And this storm actually hit at 2300 hours in reality. So KP, because 2300 hours is in the window 9 to 12, it steps up to the maximum value 2 hours before the storm actually hit. If you go to the 90-minute value, of course you're getting closer. If you're getting to the 1 hour value, you pick up the storm. And you even see if you go to 30 minutes that actually it decreases a little bit at the end of the interval. So that's additional information we have now thanks to this HP index. Forecasting drivers, very quickly. So this is not per se the thermosphere model performance itself. But when you're forecasting drag, you need a forecast of your drivers. So you have an error due to the thermosphere model itself. And on top of that, you have an error due to the forecast of your drivers. So here, F10.7, very average kind of errors, but for a one-day forecast, 1 to 4% typical error in F10.7. If you go to 6-day, it already goes up to 3 to 14%. You see, this is, of course, this forecasting performance is a function of solar activity. The higher the activity, the worse it gets. Solar cycle maximum, we have the worst prediction simply because the dynamic range of our forecasting has become so much bigger. 41-day forecast, well, you see already how big this becomes. Same thing for geomagnetic activity. So here it's shown again for it's KP again. Yesterday, it was called, what Giovanni called this summer, what did he call it? When he said artificially augmenting the number of extreme events in his database. In machine learning, actually it's called rebalancing. And so what Gabe said, so what they did in their model is indeed you have a number of extreme events in your database and you simply create 100 times more. Otherwise, through the numbers of, let's say, quiet time, the intense effects are just drowned out, and your model like focuses mostly and will have the best results for the quiet times. However, when you do this rebalancing that Giovanni didn't tell comes at a price. You cannot just add a whole bunch of high intensity effects without paying the price at low activity. So actually, when you do this, you have a better performance for storm activity, but your performance for low geomagnetic activity is worse. You can say, well, is that bad, or is that is something you have to choose. Data distribution again, just focusing on the recent data since 2000, so the high resolution accelerometer data. So this is altitude versus solar activity. You see here goes at the bottom, champ, swarm, grace. So what you see here, solar activity, low, medium, high, very high. So very high, well, there is just a few months of champ and even. The other thing that this shows, what I said, we have composition data in the 70s, 80s. So what we do now is these total densities are actually the sum of molecular nitrogen, oxygen, and helium. And so depending on the altitude, it's your model that, let's say, distributes in your residual, in your least squares adjustment, which part is which contribution. And so this sum together adds up to these total densities. But we do not have the real composition information. Another thing which will happen to, like I said, in the empirical model, because this is the backbone, the most accurate data sets we have, but they actually go from low to medium solar activity. And if you compute it right, there's even like 75% is for solar activity less than 100. So you're very, very extremely biased toward low and medium high solar activity. That is also something that you can try to rebalance that in your model fit, but it is kind of difficult because you simply do not have the information that you need to rebalance. Storms. We want our models to be as accurate as possible when we are modeling storms, when the satellite has to extrapolate through a storm, because these are the most dramatic events. This is where the orbit errors, the deviation from nominal orbit becomes biggest. But you already see why this is. This is an orbit average density. For this particular storm, you see the density increases by an order of 6.5 on average over one orbit. So that is a significant effect. But here again, we have a database that is far from complete. So this shows you again, in blue is solar activity in F10.7, and in red, you have KP. So this is the number of storms. So since 1970, we had 11 KP9 events. I'm telling here the events that we had actually density measurements available to. 35.9 minus. So you can see here, if you take it at this bottom, this top part of the plot, this is the distribution we have over time of storms. So we don't have a huge amount of storms that we actually can use to fit the model coefficients. And so our model coefficients are based on a, well, should we call it a statistically representative or maybe not representative sample? Probably not. Now in the end, what then happens? When you construct DTM, you're using solar EUV drivers, F10, F30, whatever. You're using geomagnetic drivers, and you have density data. And all these are used in a least squares fit to adjust these model coefficients. In my case, in the case of MSIS as well, solar and geomagnetic input, we consider this as truth, meaning that we do not adjust our drivers. It's justified to adjust the drivers because you know that they are proxies. So they are not right, they are not entirely correct. So the fact that you could correct for the drivers is not heresy or something, it's just that you need to, well, we need to anchor, in our case we said we need to anchor our models somewhere. So we said we're keeping this fixed. On the other hand, the density data, it is a little bit easier to know where the uncertainties and where the errors are. So the density data, we do editing. So we do thresholding, we do 3 sigma elimination, all that kind of thing. We select typically, in this example, for example, I cut off at 400 kilometers because you see that above that, the noise becomes too high in the spectrometer data. There are these scale corrections, what I explained. If you're combining data sets that come from multiple sources, you have to make sure that all the density data sets are consistent. So when you're propagating from one altitude to the next, that you're ending up each time from one data set to the next, that you don't have remaining scale factors between these data sets. But so in the end, what does happen, of course, is this. We have data, for example, only available here in the middle, or only available there, or only available there. So if, in this typical case, you're fitting your model coefficients, you have no information there, you have no information there, and at a later stage, whatever, years later, when you have new data sets, you find out that you were actually, because this regression is based on a too small, too short interval, you're underestimating, you're overestimating at low and high density. So that's why it is so essential that your database is as complete in space and time as possible, which of course it isn't, but. Secondly, if on top of that you put scale errors of your density data sets, you can have effects like this. So these are the kind of errors that are in your model that are very, very difficult to correct for. We've been trying now, we've done a full simulation of all existing data sets, so some kind of OSSI, to see what the effect is of, at least of the data distribution, on how it biases specific model coefficients. So we're going to see if that helps in the next round of model adjustments. Okay, now I can very quickly show you the eSign Center. So in the data collections, where's my thing? Wrong glasses, sorry. I'm in workflows. You have DTM. It gives you a description of what it does, what it needs as input, and what it gives as output. You can open that model. It will open it in a second screen, like Vivian showed us yesterday. You can execute the model. So if you execute the model, what's going on? This one. Enable the thing. Here are the input parameters that have been described on top, which you have to enter. So we're giving here solar activity, so that on top is the mean solar activity, daily solar activity, altitude, day of year, so the season, and the 2 values of geomagnetic activity. So this is not a particularly good example of default values, but it doesn't matter. The idea is that you choose it yourself, of course. So you can change these. You run this. It gives you this execution ID. You have to copy that, because typically if you want to plot it or if you want to download the results, You need that number. You can plot this in the next. Just to have a quick look. You can choose between composition, total density, or temperature. Enable, sorry. Let's take temperature. Oh yeah, this is it. I just told everyone. And it gives you a plot. This is just a sample plot. It's not meant for everyone to use, of course. If you want to have nice plots, you can download the data, which is below. Here the results. You have download all the results. It will give you a file that it is a zip file with all the contents of all these latitude versus local time grids. So probably won't need this for the exercises Thursday or Friday, but this is basically how it works for all the API. This is the standard API page. So, thank you.
We can maybe take